Welcome, everyone. Thanks for joining today's webinar. This is one of our most popular webinars to date. We're going to talk about NLP search, question answering systems, virtual assistants, and implementing them with deep learning. I'm Andrew Oliver, Lucidworks Director of Product Marketing. Our speakers today are two of our data scientists, Sanket and Sava Kalbachou. As we go through the talk, please feel free to ask questions. Type your questions into the chat box on the bottom left side of your screen, and we'll answer a few of your questions at the end of the webinar. If we don't get to your question today, a member of the Lucidworks team will reach out to you. Before we begin, I want to mention not to worry. Whether you're a deep learning expert or a business expert looking to see how these technologies can work for you, we have you covered. Part one of this talk is general enough for everyone. We'll cover the why and what for of these technologies. Part two of this talk gets a bit more technical, and we'll talk about the benefits of different implementation methods and models. If you're interested in getting up to speed with these AI and deep learning concepts, check out our new YouTube channel called Lucid Thoughts. This is a new video series that will help you come up to speed on these hot topics. Now, without further ado, let's jump right in with a general question from one of our speakers. Sanket, tell me, why do we need this question answering stuff instead of just normal keyword search?
Great question, Andy, and thank you for having me here today. The main motivation behind a question answering project is today the expectation of the users when they ask a question is to get a direct solution to it. Those days are gone when people would be happy if you give a relevant doc which has the solution. A typical example is, how should I attach a child seat to my 2014 Honda Civic? I have already given you all the specifics of my problem, and if you point me to a 100-page manual, it's not going to work for me. What I'm really looking for is 5 to 10 steps of installation. Our attempt here is to answer the questions in the best possible way and to move beyond the realm of document search. So you might ask, why haven't we been doing this all along? Recent advancements in the compute power and powerful GPUs allow us to train complex neural network architectures and leverage huge amounts of data we produce on a daily basis. The amount of data needed to train good quality deep learning models is huge. It varies from like millions to billions of data points. However, we don't have to start from scratch. Transfer learning is a concept which allows us to reuse the models trained by companies like Google and Facebook for our use cases with small amounts of training data. These advancements in technology and science make it a perfect time to solve challenging tasks like a QA system. A question answering system can be categorized into 3 classes. The first class is information retrieval based. These are systems where you search for answers in unstructured documents. The second type is a semantic parser-based system where you convert natural language queries into SQL queries and query a relational database. For example, what is the stock price of Apple today? The third type of question answering system is a knowledge-based system where you build ontology and graph systems and use the relationships between the vertices of the graph to find an answer. Semantic knowledge graph is an example of such a system. Today we are going to focus on the information retrieval based QA system and look at the components required to build that. Before we look at the demo and dive into the technical details, let's first discuss the business goals and implementations of this tool. There are 2 areas where the system can have the maximum impact. First is to implement on the help or support pages of customer-facing websites and attempt to provide direct solution to their problems and save time. We can also show them similarly asked questions which have already been answered, something like you would see on Quora. This also guides the user's curiosity and helps them know the product and the company better. Also, you can ask the same question in many different ways, and there are chances that we might have already answered it. We are not just talking about same keywords. It could also be framed using synonyms and interchangeable words. So whenever a customer is typing a question, we guide them to frame the question in a way that we have already answered. This helps reduce errors, and the QA system has a higher chance at being accurate. The second business area in using it is an augmented intelligence system for the backend support teams. We have observed with many customers that they have small groups within the support team who specialize in certain areas of businesses. The problem comes when they try to scale up the support team. It creates an imbalanced workload distribution and is not an optimized way to operate. A QA system will help redistribute the knowledge in a smarter way across the support team by providing solved reference tickets to the agents and help them tackle the current problem. You would be able to club together similar issues and assign it to a specialized person. And you can do many more such optimizations. Typically, when new persons are onboarded, it takes significant amount of time for them to be very productive. If they have some system like QA system with Fusion, we can reduce that gap and bring them up to speed as quickly as possible. And they will be able to discover the valuable knowledge of the organization has had in a very relevant and efficient way. Overall, in the long term, you can expect to save a lot by keeping the customers happy and at the same time, exponentially increasing the productivity. Beyond the support teams, some of the interesting use cases are in the e-commerce domain, curating question answers from product descriptions can prove extremely helpful. And in the pharmaceutical domain, you can expect such a system to help not just the support team, but the doctors too. Another important question I get asked is what kind of data is needed for this system? So we can use all the historic support tickets, FAQs, user engagement logs referred as signals in Fusion, etc. There are also ways we can look at the logs and curate FAQs. If you closely observe your data, almost always there is a pattern which points to an unanswered question of the users. And we have experts at Lucidworks who can do such an analysis and provide insights to utilize the QA system to its fullest potential. And before we dive into the architecture and deep learning models, let's take a look at the sample QA system we built around the insurance domain. The data we have used consists of about 30,000 answers provided by the community. The data is used for training is in the format of question and answer pairs. So here is the first example. Can my wife drive on my insurance? On the right panel, you have the most relevant answers to the current question. The models are choosing these answers among a pool of 30,000 possible answers. And these answers are from different insurance topics like home insurance, auto insurance, health insurance, military insurance, etc. Overall, it provides very accurate results. And we'll discuss the matrix as we proceed in this talk. On the left panel, you have similarly asked questions by other users, and you can see that our models are generalizing very well. It understands that spouse, wife, husband, and girlfriend are interchangeable words and can be asked in a similar fashion. Let's take a look at another example. Is it compulsory to have homeowners insurance? So if you look at the results, again, the models find very good results at the top. You can see that homeowners insurance is not mandatory for those who don't want to be covered against fire, wind, theft, etc. Also, if you look at the left side, we have like very generalized questions. It understands that is it mandatory to have homeowners insurance? So this is a question that someone has already asked us. The models understand that mandatory, compulsory are like interchangeable words. And if you go down this list, you will see that it asks a similar question to this topic is it a legal requirement to have homeowners insurance? This is a perfect example of what we mean by guiding the user's curiosity. So if you were an insurance company and provided such a system, It could really help the users make informed decisions about what insurance they should purchase. So if they think that, oh, this is something interesting for me to know, so you can just immediately show them the results on the spot without having them to go through your support channel and wait for like a couple of hours to get the results back. So now that we have seen the use cases and the sample question answering system we built, Sava will walk us through the architecture of the system. Sava?
Thanks, Sanket, and thank you everyone for joining. Now let's go deep into technical things. Our workflow consists of 2 steps that allows us to get the best results as possible using a reasonable amount of resources. Firstly, we do candidates retrieving using Solr. It's very fast and scalable, allows us to search across the whole space of documents. This step is responsible for achieving high recall. Then we apply LTR model to re-rank top-end candidates that we previously got from Solr. It might be classical machine learning models like XGBoost or something more advanced like deep neural networks. This step is responsible for achieving high precision. Number of candidates that are used for re-ranking is choosing based on model complexity and available resources. Unfortunately, we cannot just easily apply a deep learning model to the whole set of documents, as it's usually very computationally expensive. So that's the reason why we have such 2-step workflow that provide us a good trade-off between high results and resources needed. Now let's take a look on feature engineering and how it's done in Fusion. Although deep learning models can be self-contained, such features might help you to get even better results. Moreover, features are usually model agnostic and might be used in other models or by their own. As many of them are computationally expensive, it makes sense to pre-compute and store features during index time by using index pipeline. So then we will need to extract features only for incoming queries during query time. Common NLP features like part of speech and named entity recognition are incorporated to the NLP annotator stage. Those annotations are indexed as Solr overlapping tokens. Word2Vec is a new stage implemented in Fusion, which runs pre-trained Word2Vec model on text to get its vector. It indexes vectors as an additional field. We have a bit more stages in query pipeline. First of them is query expansion. It might leverage domain-specific synonyms and answer type classifiers to enrich incoming queries. We also developed an unsupervised algorithm that finds associations between the keywords in questions and answers using model informational store. Next stages are similar to what we already saw in index pipeline. It's NLP annotator that does NER and POS extraction for incoming queries. And next, Word2Vec stage that computes cosine similarity between question and answer vectors. All these things are then used as features. Now we can hit Solr and get a candidate pool of documents and generate LTR features for it. After that, we have a custom feature generation stage where we extract more granular and specific features, like how many URLs are there, number of question marks, etc. Finally, we have the features ready, and we can use them in our machine learning or deep learning models to re-rank results. Here is how it looks into the Fusion UI. For example, web page of NLP annotator stage. This stage now allows you to choose either OpenNLP or SparkNLP to do the POS, NER, and sentence detection. You can specify the input field to annotate and the annotator type. Next, in the pipeline, we have the extract nouns and verbs stage and some other standard query stages. Here is UI of Word2Vec stage, which computes cosine similarity between question vector and answer vectors. And finally, the LTR stage, which uses ML model stored in the blob store to do re-ranking. Now let's dive deep into exact question answering modeling. As it usually happens, all solutions start from the available training data. In our cases, it might be support archives, email threads, existing FAQs, forums, or even Slack conversations. For R&D purposes, we use insurance QA dataset, which consists of real user questions and high-quality answers from professionals with deep domain knowledge. About 13,000 questions and 21,000 answers were used for training. But what if you don't have any labeled data for training? Well, then we still can use variety of unsupervised methods. In our experiments, they showed the best results for question-question similarity task. For supervised model, we use XGBoost with heavy feature engineering and triplet-based Siamese deep neural networks. Unsupervised modeling was done by using classical approaches as well as the newest, fanciest methods like Google Universal Sentence Encoder. Output of some of the unsupervised models was then used as features to our supervised models. For example, here is a feature importance output from XGBoost model. It shows that such unsupervised features like cosine distances between different question and answer vectors are very important, and model pays a lot of attention on them. Now let's focus on the Siamese deep neural network architecture that we used. The main part of it is a deep neural encoder. Its goal to map incoming questions and existing answers or existing questions to the same vector space. Training is done by using triplets, which means that as input we have question, positive relevant answer, and negative irrelevant answer. Each of them is then encoded to the same vector space using our shared DNN encoder. Cosine distances between question vector and both answer vectors are calculated and compared in a triplet loss function. The idea behind that is to help neural network to learn how to map questions and relevant answers as close as possible to each other, but questions and irrelevant answers as far as possible from each other in the same vector space. Here is how our shared DNN encoder looks like. So, for example, when a new question comes, it's firstly tokenized, then tokens are mapped to indexes in embeddings layer, which is kind of lookup table. This embeddings layer is initialized with fast text vectors retrained on both Wikipedia and Common Crawl corpuses. Then we use some regularization, which is spatial dropout 1D layer in our case. It prevents overfitting of our DNN. After that, we use bidirectional LSTM layer, which goes forward and backward of our sequence of embeddings and compute deep complex features for each of the words. cuDNN LSTM version was used as it allowed us to do fast experiments. And finally, as a global pooling, attention-weighted average mechanism is used. It outputs final dense vector, which is deep representation of our question in some vector space. So now, as we have our DNN shared encoder trained, we can encode our existing answers and index obtained dense vectors. Then, when new question comes, we encode it to the same vector space and use KNN-like methods to rank answers. It allows us to boost those that are more relevant to incoming questions. Moreover, as a great additional side effect of proposed training, we can apply the same workflow to rank existing questions. So we get question-question similarity model for free as well, without any retraining. Here are results that we got on holdout test set. They show that there is a reasonable gap between XGBoost and deep learning model. Moreover, for deep learning model, we just used raw text, whereas for XGBoost, lots of features were designed and generated. We also tried to use deep learning model output as additional input feature to the XGBoost model to make some kind of models ensemble, but it didn't give us any reasonable boost. This allows us to make conclusions that deep learning models are already very self-contained. Also, you probably often heard that deep learning can be used only if you have lots of training data. But here we show that it's not always true. Although accuracy of deep learning model drops when it's trained using 50 or 10% of training data, it is still better than XGBoost model trained on the whole training dataset. This is due to the recent achievements in transfer learning, which allows us to leverage knowledge from already pre-trained models, which is post-text embeddings in our case. To conclude, deep learning models provide much better results than traditional models when you have enough training data. When the training dataset is too small, like 3,000–5,000 QA pairs, results are pretty similar, and traditional methods look more attractive as they are less computationally expensive. There is also a huge gap between supervised and unsupervised models. But anyway, some of unsupervised methods or ensemble of them might be used as additional features for supervised models or for some initial modeling, especially when they are applied to the question-question similarity task, and such tools like Google Universal Sentence Encoder are used. So thank you again to everyone for joining, and that concludes our presentation.
Thanks, Sava and Sanket. As you can see, this is a powerful tool to make information a lot more accessible to employees and customers alike. It's also a somewhat complicated field that the team in Lucidworks is working on in order to make this accessible to more people. It's personally my New Year's resolution to bring more AI concepts and technical know-how to you, our audience. So definitely check out our YouTube channel, Lucid Thoughts, in order to prepare yourself. Lucid Thoughts explains AI concepts at an accessible level for everyone. However, we're also going to be diving into deeper concepts like we did in this talk. So if you're not on our mailing list, please feel free to contact us. Stay tuned for more webinars, events, and other AI learning opportunities. Now, without further ado, let's answer some questions. We have a few already, but if you have any questions, please add them in the chat box and we'll do our best to answer them on air. So here's our first question. What publicly available models do you recommend for transfer learning?
Well, in NLP, mostly it is already pre-trained embeddings like GLOF or FastText. I would say FastText are more robust and provide better results, so you can start with them. There is also recent advanced methods like language modeling, which would use the whole neural network already pre-trained, but they usually require more work to do and are more complex.
Great, thanks. So our next question is, LTR requires document engagement data. How do you have that before the system exists?
That's the input to our entire system, right? Like, for example, the historic question answering pairs. So whenever people come to your support channel and ask a question, someone has replied to that question, right? We will use this data and index it into Solr and then build our models on top of that.
Outstanding. So our next question here, how deep is the triplet neural network?
Experimented and found that just one bidirectional LSTM layer is enough for us. So it's like it was on the picture, it's embedding layer, then one bidirectional LSTM layer, and one attention layer that outputs the dense vector for incoming questions or answers.
Thank you. So the next question we have is, how many negative or irrelevant answers do you give the encoder when teaching the model?
So we start by training it with one positive example and 15 randomly selected negative examples. So that's how we start the training. And one thing that we were concerned about is whether it would create an imbalanced data set to train on. But it turns out that we are actually training the model to learn the embedding vector space. So when we give like 15 negative examples, it learns to separate away the correct answer from the incorrect answers, like all 15 different varieties of answers. So that provides like a better way of training it. But the short answer is we use 15 negative answers.
Great. So there's a question about the NLP models that you talked about. Can you spell those out or make it clear which models those were?
So with the NLP modeling, you mean there are like different stages for NLP. We do the parts of speech tagging, and then we do the named entity recognition. We use Spark NLP there, but we also have an option for Open NLP in Fusion. So Spark NLP is an open source project on the web, which has been very popular in recent days. And it's also based on top of like deep learning. They train their TensorFlow models and use it inside there.
All right, outstanding. So another question. Do you need to know any of the linguistics knowledge to apply this to a language other than English?
I think it's more about the tokenization of the data. For example, you definitely need to know how the data should be tokenized. So for example, Chinese tokenization is totally different than English tokenization. So that's the biggest factor. And then you really don't need like much of the grammar knowledge about the language once you have the tokenization in the right way. Also, when these models are trained, they learn the features by themselves, like the arrangement of the words, etc. So one wall someone might hit is all the embeddings layer that we use is initialized with fast text embeddings. So we are leveraging huge amounts of like data that has been trained, like a network that has been trained on that by Facebook, and then we are using that and building on top of that. So that's why we get very good quality with less amount of data. So if you have to start from scratch for a new language, if you have enough amount of data, definitely this is doable with a good quality.
For sure, you need to use pre-trained embeddings from this language, but not just from English.
All right. So another question, or how long did it take to train this, and are you able to distribute the training process?
We haven't tried to distribute it on multi-GPU or multi-servers, but yeah, it's feasible to do. But overall, yeah, it took just an hour or a bit more on a single GPU to be trained.
Outstanding. How is this different from, say, chatbots?
Yeah, so chatbots are kind of a virtual assistant that are expected to answer questions like humans. But the fact is that most of them are template driven and have a fixed flow of dialogue. Current state is that they don't generalize well and are good for simple tasks like reset my password, etc. But a QA system that we have focused on is a smarter way of searching, and it can be integrated inside a chatbot or a virtual assistant, or it can be used as a standalone system. So chatbots are more of an interface. However, a QA system is more of the back-end engineering task, which is like a solid core of search plus machine learning. And we also have like a fallback strategy in a QA system, which a typical chatbot doesn't know. If something comes up to a chatbot which it cannot handle, it will just give up and say, I cannot handle it. However, we will try to attempt and do a regular search if our deep learning models are not confident enough to answer the question. So on the customer-facing side, it can be integrated with a chatbot. So a chatbot and a QA system can be merged together to make the interface good and also provide good quality results. And for the support teams, you really don't need the chatbot part. You can just keep the QA system as a standalone thing.
All right, thanks. How would you go about creating a Word2Vec for an unsupervised collection stored in Solr?
Generally, Fusion has Word2Vec Spark job that uses your collection and trains Word2Vec model. And then it is applied in those Word2Vec stages that I have been talked about.
All right. What are the benefits of using Solr as a backend storage?
Yeah, go ahead, Sanket.
Yeah, so Solr is really amazing at doing like fast retrieval of documents, even at scales of like millions of documents. So it's in like milliseconds. So when you have like large amounts of data, applying deep learning on like by itself on all of this data is going to take more time than the user can wait at the website to get the answers back. So what we do is we first go to Solr and get the candidate documents fast, and then re-rank them on a shorter scale. So we reduce the search space of the deep learning models by leveraging Solr's speed. So that's how we are using Solr there.
All right. How does the system learn to re-rank the answers based on user behavior while interacting with the results?
Fusion also supports signals that allows collect actually signals like clicks of users if they choose like one answer or another, you know, when they were searching. So then we can use those signals, we can aggregate them and enrich our model.
And this also serves as a validation step for our models. So the answers that we show on the top, are people looking at them? Do they click them? Or whether they click the third answer, or that you can extract like valuable information out of that and improve your models on top of it.
All right, great. So next question, how much would using ML stages in the query pipeline slow down the speed of retrieval?
So query pipelines work after we have retrieved documents from Solr. So if you have Solr tuned in the best optimal way using replicas and sharding, then it's going to be at milliseconds level, and the ML stages will add like 30 to 40 milliseconds extra on top of it. So our attempt here is to like keep it as low as possible here. So for example, if you have a leeway of like 300 milliseconds for the ML stage to run, well, then let the deep learning models look at 2,000 documents instead of just like 500 documents. So how many documents do you let the deep learning models look at? That determines how long it's going to take to compute it.
All right, and here's our final question that we have time for today. Have you tried the BERT model, B-E-R-T, all caps, instead of fast text?
Well, BERT model was just released recently, maybe last month or so, and it's actually a language model, you know, that's I mentioned answering another question. We haven't tried it yet, but in general, it would work much slower, fortunately, than our way, just because it's a very, very big and deep model that attempts to solve everything at once. Yeah, but we are really looking forward to, you know, experiment with it and to play with it.
Outstanding. So that's all the time we have for questions. So thank you, guys. If we didn't get to your question today, a member of the Lucidworks team will follow up with you offline. Thanks again to everyone for joining. Thanks to our speakers, Sanket and Sava. Stay tuned for more webinars on our website, and we'll see you next time.
Thanks, Andy, and thanks everyone.
Thanks, Andy. Yep, thanks to everyone.